This is a 5-minute introduction on this paper. Video data has taken more than 80% of the internet traffic, and video compression aims at reducing the size required for storing those videos. Nowadays, people still rely on traditional non-deep learning methods for encoding the videos, and there are lots of good standards proposed all the way to H.265. On the other hand, deep learning has been widely used for lots of computer vision tasks because of its powerful representation ability. So our question is, what will happen if video compression and deep learning can be considered together? Before this work, there has been deep learning methods for image compression, but they ignore temporal redundancy, and there has been deep learning method for video compression, but they are not end-to-end. In this paper, we propose the first end-to-end deep model for video compression. This is the paradigm for traditional video compression methods. First, suppose that we have several frames. As an example here, if we have 2 frames, we can estimate the motion between these 2 frames. So for the current frame, if we have the motion of the previous frame, we can warp the previous frame as the estimation of what could happen for the current frame. So together with the motion and previous frame, we have the warped frame, and the difference between the warped frame and current frame becomes the residual. And in traditional non-deep learning methods, we will use transform to encode those residuals. And for residuals, we will undergo linear transforms like discrete cosine transforms, and then quantize those transformed results in order to obtain the compressed data. And we can also have inverse transform and reconstructed residual to have the reconstructed image when consider the warped frame together. And then we will have the entropy coding to encode those data into bit streams. Our deep learning framework is inspired by the traditional designs, but we will replace all those designs by neural networks, by subnetworks, because our network is a single deep network that can accomplish all the goals. For example, for block-based motion estimation, we will replace it by optical flow estimation network to obtain the motion. And we will also have the motion vector encoding network to encode the motion. And then we have the decoder net to obtain the decoded motion. With the decoded motion, we can do the compensation to predict what could happen for the current frame from the motion and the previous frame. And we also use a network to achieve this goal. After we have the predicted result, we will calculate the difference between the predicted current frame and the real current frame to obtain the residue. And then, instead of using discrete linear transforms, we will use residue encoder network to encode those residues by using a deep model, and then corresponding quantization will be done. And for entropy coding, we replace it by bitrate estimation network to estimate the possible bitrate so that we can facilitate the entropy coding. And the whole network is learned end-to-end using a single loss function that uses distortion and rate as the loss. On the HEVC Class B dataset, we conduct ablation study showing that starting from the baseline, if we can estimate using motion compensation network, joint training, motion compensation network, motion information, and buffer update, we can consistently improve the results. And the results on UVG dataset shows that our proposed model has performance that is close to H.265 in terms of the PSNR and MSISSIM for higher bit rates. When the BPP bit rate, bits per pixel, is larger than 0.1.